Hello, welcome to all. In the previous lecture, we completed the electrostatics. Now, in the present lecture, we are going to start the magnetostatics. Yeah, electrostatics and magnetostatics are very much similar. Okay, the terminology will be similar. Not only this, but we have some deep connections between electricity and magnetism, or electrostatics and magnetostatics. Okay, now I will give you the outline of today's class. Okay, first of all, we will study the Oysters discovery, magnetic force, magnetic field, magnetic flux and magnetic field. That means the relation between these two things. Okay, this is the plan of today's class. Okay, right. Yeah, what Einstein discovered in the early part of the 19th century, there is, there is some induced magnetic field around the current carrying conductor. Okay, whenever you place a magnetic needle in the surroundings, in the immediate surroundings of the current carrying wire, you observe the deflection of the magnetic compass. What is the meaning of that? Magnetic compass only responds to the magnetic field. Then where is the magnetic field? Just current is flowing through steadily through that wire. So what is the meaning of this? What is the reason for the deflection of the magnetic needle? Because the current carrying conductor is inducing the magnetic field around it. Magnetic field around it. This was the very important discovery made by the Einstein in 1820. Okay, yeah. So far people considered electricity and magnetism as two separate branches of the physics. But now, after the Einstein's discovery that current flowing steadily through a conductor can produce the magnetic field, the magnetism and electricity are not different entities. Both are the same. Both are connected with each other. Okay, that's why uh, we call the subject electromagnetism. Electromagnetism. Okay, yeah. So this is an important discovery which relates the electricity and magnetism directly. So what is the truth revealed from the Einstein's experiment? A current flowing steadily through a wire is able to create the magnetic field, its own magnetic field. That's why in that experiment the magnetic needle is deflected. So so people understood that currents can also create magnetic fields. So in the previous classes, we studied electricity and magnetism separately. Now we are studying the magnetism after studying the electricity. Why? Because this electricity is the cause of the magnetism. So from the same point of view, we proceed uh, to study the magnetostatics. So we start from the uh, electricity. So at the bottom of this magnetostatics, there is electrostatics or electricity or the charge carriers. Okay, we will continue this view while starting the magnetostatics. Okay. Now, see, instead of electric field, you have magnetic field. This is electrostatics. This is electrostatics. This is magnetostatics. See, in the place of E, you get B, capital B. Okay, right? Here, in electrostatics, you have electric field. Okay, Fe. In magnetostatic, electric force. Okay, electrostatic force. Here, in magnetism, you have magnetic force, Fm. Fm. Okay. In the place of capital E, you have capital V. That means in the place of electric field, you have magnetic field. In the place of electrostatic force, you have magnetostatic force. Okay, what is the source of electric field? Stationary charge. Okay. Okay. Charge. Actually, whenever you study the magnetism as a separate branch, the place of Q is occupied by the pole strength. Small m, this is pole strength. This is pole strength. Of course, we will not go for this pole strengths and all these things. Why? Because we do not take the natural bar magnets or also magnets for the creation of the magnetic field. Okay, we are creating magnetic fields through the current. Okay, right. Next, here in electrostatics you have permittivity of free space. In magnetostatics you have permeability of the free space. Okay, so here you have some corresponding quantities to the quantities that are there in the electrostatics. So what are the most common things? Force and field. In electrostatics you have electrostatic force. In magnetostatics you have magnetic force. In electrostatics you have electric field intensity or electric field strength. In magnetostatics you have magnetic field, or it's actually magnetic induction vector. B's. Okay. Now in electrostatics you have electric field lines. In magnetostatics you have magnetic field lines. So there also you have field lines. Here in magnetism also you have field lines. Okay. In electrostatics, field line is an imaginary concept. Here also it is an imaginary concept. But here we have to change the definition of the field line. Okay. Field line is the path of the unit positive charge moving in the electric field. Here the field line is the path of the North Pole moving in the magnetic field. So here positive charge place is replaced by the North Pole. Okay, here you have two polarities: positive charge, North Pole; negative charge, South Pole. Okay, right? In electrostatics, field line starts from positive charge and terminate in negative charge. In magnetostatics, magnetic field lines and force lines start from north pole and terminate in south pole. Okay, these are all the similarities between electrostatics and magnetostatics. Okay. See, the electric field is also represented by force lines or field lines. Magnetic field is also represented by the force lines or field lines. Okay, these are all the similarities. We come to the force lines and flux and magnetic fields later at the end of the class. Okay. Now, at the beginning of the class, let us try to give the definition of a magnetic field B by making use of the formula for the magnetostatic force, okay, or the magnetic force, or the we call that as a part of Lorentz force. Okay. See, whenever there is a magnetic field, whenever there is a magnetic field, you observe the magnetic forces. Within the magnetic field, you have within the magnetic field you have magnetic forces. Okay, right. Magnetic force F acts on a bar magnet or a magnetic force. When you bring the external bar magnet into the field of some other magnet, then the poles of that magnet will be acted upon by the magnetic force. That is one thing. Okay, in addition to that, here, whenever you bring a moving charge into the magnetic field, external magnetic field, then also your charge will experience, the magnetic force. Why the magnetic field is acting on the charge in motion? Why? Because charge in motion means a current. These currents are also creating the magnetic fields. So that magnetic field interacts with the external magnetic field. Okay. Experimentally, it is found that force acting on a charge Q is given by, see, what is the electrostatic force? If you place the Q charge in the external field E, how much electrostatic force it experiences? QE. QE. Okay. Right. Now, external field is a magnetic field. Okay. Magnetic induction. Okay. Whose magnitude is B. So, in that magnetic field, you are placing a charge Q. Then, F magnetic is given by Q V cross B. Q V cross B. Q V cross B. Fm magnetic is equal to Q V cross B. Okay, V is a vector, B is a vector. Yeah, this is the formula giving the magnitude of the magnetic force acting on a charge placed inside the magnetic field. Magnetic field. Okay. Okay, one thing you see in the slide, what is the direction of the induced magnetic field? We are already discussed about the induced field of the current passing through a wire. Okay, the direction of induced magnetic field is given by the right hand thumb rule. Okay, you just take the wire and you just hold the wire with your right hand by curling your fingers around the conductor. Okay, suppose that okay, you are holding the wire like this. You see, your thumb is pointing upwards. Okay, the direction of folding of your fingers is a magnetic is a direction of magnetic field for the current flowing from the bottom to top. Okay, whenever the current is flowing upwards in the conductor, then that means current is flowing in the direction of your thumb, right hand thumb. Then the direction of your fingers will give you the direction of induced magnetic field. That you can see in the slide also. Okay. Yeah, this is about a right hand thumb rule giving the direction of the induced magnetic field. Okay. Yeah, see around the bar magnet you will see the field lines, magnetic field is there. Okay. In such a field we are placing a charge. We are placing a charge. This is the external field. Okay. See, you can see here the field lines are starting from the north pole and terminating in the south pole. Okay. Yeah. Now let us come to this magnetic force and the definition of B from this magnetic force. Actually, we define B by using this relation. First of all, let us see what is this relation. Here, this will give you the magnitude of a force or the direction. Okay. See here, this is a cross product. This is also a vector. Okay. Of course, you will find the magnitude of F as well as the direction by using this relation. Okay. Yeah. Now, you know the magnitudes. Okay. You have to just expand this. Okay. After expansion, you will find uh, just if you want to take the magnitude, Fm is equal to Q V B sin theta. QVB sin theta. Okay. Okay. Right. This is the scalar equation. This will give you the magnitude of F. But this equation gives you the direction of a magnetic force acting on a charge. Okay. First of all, let us talk about the magnitude of the magnetic force. It depends on magnetic force depends on the charge. Okay, non-zero charge. Okay, it acts on a charged particle. Okay, but here what is V and what is B? Here, otherwise where Q is a charge. Q is a charge. Yeah. B is a. Otherwise I will write here. B is a magnetic. B is a B is a magnetic induction or magnetic field. Okay, and theta is the angle between two vectors v and b, between v and b. What is v? The direction of the charged particle. V is the velocity. Okay. What is v here? Velocity. Okay. If you want, you write here v. Yeah, you write here v is the velocity of the charge. V is the velocity of the charge. Okay. Right. Q is the charge, V is the velocity of the charge, and B is the magnetic induction, and theta is the angle between V and B. Okay. That means V gives you the direction of motion of the charged particle. B is the direction of the magnetic field. Okay. Direction of the magnetic field. In how many ways we will show the direction of the magnetic field into the paper, onto the paper. This gives you the field direction into the board, into the paper. This gives you the into the paper. Okay. This gives you the direction of magnetic field outside the paper. Okay. Outside the paper or the plane. Okay. Yeah. We will indicate like this. Cross is there means you are just irising the arrow into the board. Okay. This will give you the direction of the magnetic field inside of the board. Next, this will indicate you that the arrow is coming from outside. Just you can see the tip here. That means magnetic field is perpendicular to the board and coming out of the board. Okay, right. This is the notation we use for showing the direction of the magnetic field. Okay, direction of the magnetic field. Right. Now, yeah, let us see the magnitude of magnetic force. It depends on Q, it depends on V, it depends on B as well as sin theta, means the angle between the magnetic field and the direction of motion of the charged particle. Okay, theta is the angle between the magnetic field and the direction of motion of the charged particle. Okay. Yeah, F depends on all these things. It depends on Q, it depends on V, it depends on V, it depends on theta. So, next, what happens if you change the theta? If you take theta is equal to 0, okay, otherwise I will write the formula here. F M is equal to QVB sin theta. F is equal to QVB sin theta. If theta is equal to 0, if theta is equal to 0 degrees, then Fm is equal to QVB sin 0. This is QVB 0. Why? Because sin 0 is 0. So this is equal to 0. So magnetic force will be 0. Magnetic force will be 0. If this is the direction of the magnetic field, and if suppose that your particle is also moving in the same direction, then the force or is a charge. Okay, the force exerted by this field on this charge is 0. Yeah, let us see now the second case. If theta is equal to 90 degrees, then what happens to this Fm? Fm is equal to QVB sine 90. Since sine 90 is 1, you have QVB into 1. Therefore, Fm is just QVB. Okay, you try to compare this two magnetic forces. In case of theta is equal to 0, you have minimum magnetic force. In the case of theta is equal to 90, you have maximum magnetic force acting on the charge traveling with the velocity v. Okay. See, let us okay, I will write here. See, this is say this is the magnetic field direction. Suppose that your particle is moving like this. Okay, with velocity v, this is the direction of b. Then how much force will act how much force acts on the charged particles? Charged particle q. The force acting on the charged particle is maximum force acts on the charged particle. Maximum force acts on the charged particle. So, whenever the angle between the direction of motion and the magnetic field is 90 degrees, then the maximum force acts on the charged particle. Okay. Yeah. So, whenever the particle moves in the direction of magnetic field, you have minimum magnetic force, that is 0. So, whenever the particle moves perpendicular to the external magnetic field, then the maximum force will be applied on the charged particle. Okay. This information can be extracted from this equation, magnetic force equation. What is the direction of magnetic force? Yeah, in case of electric force, you have F is equal to QE. Okay, it is very easy to find the direction of electric field. Why? Because direction of E is the direction of F. But here, your magnetic force is expressed as some cross product with the field. Okay. Now, to determine the direction of the force will be somewhat difficult. Here, you may use the right hand screw rule or right hand rule here. See, whenever you take your right hand and suppose that your fingers are taking v vector onto b vector, onto b vector. Okay, suppose that this is b, this is v. Your fingers, suppose that this is b, this is v. Your fingers are bringing that v vector onto the b vector. Then, in that case, the direction of force will be along your thumb. Okay, your fingers are bringing the v vector towards b vector. In that case, okay, the magnetic force direction will be upwards. Okay, you can see this in the slide also. See here. You may bring the v vector onto the B vector by using your fingers, okay, then the direction of thumb will be the direction of the physical quantity, which is the cross product of those two physical quantities, here V and B. Okay, in general we may apply this for any cross product. Suppose C is equal to A cross B. Okay, if your fingers are bringing A vector onto B vector, then your thumb direction will be the cross product vector. Here our cross product vector is a magnetic force, so you may apply this. Okay, you may apply this right hand um, screw rule. Okay, right. Here you see in this diagram, okay, the magnetic field is horizontal. Okay, a particle is moving like this in the vertical circle. Okay, here we have to find the direction of the magnetic force acting on the charged particle. Okay, see, you see the charged particle, the magnetic field is like this. Okay, now the particle is rotating like this. Okay, at some moment you may have the direction of V like this. Okay, suppose that both are in the same plane. Okay, both are in the same plane. Now what happens here, if you try to bring this V vector onto the B vector with the help of your fingers, with the help of your fingers, V vector onto B vector. Okay, you are trying to bring the V vector onto the B vector. What happens here? The magnetic force direction will be given by your thumb. Okay, you see here you are bringing this V vector onto the B vector. So in this case your thumb is pointing inside of the bowl, So in this way we can find the direction of the magnetic force acting on the charged particle. Okay, right. Yeah, here in this slide you can also see the another method to find the direction of the magnetic force. Okay, here you are only using only three fingers. Okay, forefinger, middle finger and thumb. Okay, here you are placing your forefinger along V and the middle finger along the B. Okay, you are aligning B along your middle finger, you are aligning V along your forefinger, and in that and you are seeing that all the three fingers are perpendicular to each other. In that case your thumb will be pointing the direction of magnetic force. Okay, here if you place your two fingers uh, in one plane, okay, that means a plane which is immediately before to you, then your thumb will point towards you. That means here the force vector will always be perpendicular to the plane in which two vectors V and B present. Okay, that is what we have to note. That applies for every cross product, not only the cross product of V and B. Okay, you may find the direction of magnetic force in this manner also. What you have to do, you have to place all of your first three fingers perpendicular to each other. You have to uh, you have to place the magnetic vector along your middle finger and velocity vector along your forefinger. Then the thumb will give you the direction of a force acting on the charged particle. Okay, this is another way. This is another way of finding the direction of a magnetic force, which you can see in the slide. Okay, right. Now here, this finding the direction is very important. Direction of the magnetic force is very important. Of course, we will be discussing in detail about this later while discussing the motion of the charged particle in the magnetic field. Okay. Right now, here we are considering this expression in order to define B. Okay. Right. See how to define. Let us write the full equation. Fm is equal to Q B uh, B VB sine theta. Then this is simply Q VB sine theta. Fm is equal to. So now what is your B magnetic field? Magnetic field can be defined as Fm magnetic force, okay, by QV sine theta. QV sine theta. QV sine theta. Okay. See, whenever your theta value is 90 degrees and all these things are of unit quantities, then what happens to you? What happens? This just magnetic field is just the magnetic force. Okay, this is the definition, very much similar to the electric field. Okay, electric field is nothing but the electric force. Here also, magnetic field or magnetic induction is nothing but the magnetic force whenever you make all these things as unit quantities. Okay. These are the similarities between the magnetic field and electric field. Okay, right. Here we are defining this B in terms of the charge, in terms of the electric charge. Okay, this is another way of defining this B. Actually, usually how do we define B when we do not consider the charges? Whenever we take we deal magnetism separately, there we define B to be the force acting on the unit north pole. Unit north pole is known as a magnetic induction, capital B. Okay. Force acting on the unit north pole is known as the magnetic induction. This is a very traditional definition. This is what we are giving the definition in terms of electricity, charge, electric charge. Okay. This is here. This is the force acting on the electric charge. Okay, force acting on the Fm is a magnetic force acting on the electric charge. Okay, whenever you take 1 coulomb charge, whenever you take V is equal to 1 meter per second, and whenever you set theta is equal to 90 degrees, then force acting on this unit charge is known as a magnetic force acting on that unit charge is known as a magnetic field or the magnetic induction. Okay, this is what the definition of B. What are the units of B? SI units, Tesla. Okay, Tesla. Units for the magnetic induction are Tesla. Okay, right. Okay, and this is about the definition of magnetic field or magnetic induction. So what are the two definitions? One is the force magnetic induction is nothing but the force acting on the unit north pole placed in the external magnetic field. Okay, right. In terms of in electric terms, how do you define this magnetic field or magnetic induction? Here, whenever you take the unit 1 coulomb charge, whenever you take 1 coulomb charge traveling with the unit velocity in the direction perpendicular to the magnetic field, then the force, magnetic force acting on the charge is called as the magnetic induction of the magnetic field. Okay, this is another definition. Okay, yeah. Next, let us go for the magnetic flux and the relation between magnetic induction and magnetic flux. Okay. Okay, right. Whenever you have magnetic field in some place, there you can imagine the magnetic force lines, the magnetic field lines. Okay, these are all these lines are imaginary lines. Imaginary lines. Okay, to show, we imagine these lines to show the presence of the magnetic field. Okay, now on what factors we have to see on what factors this magnetic flux depends. Okay, see, what is flux? Flux means magnetic flux means magnetic field lines passing through some particular area inside the magnetic field. Magnetic field. Okay. Suppose that you are taking, this is the magnetic field. You are taking some unit area. Okay. Unit area. Some area. You are taking some area ds. Okay. See, what happens when you increase this ds? If you increase this ds, many lines of force pass through it. Okay, so your phi is proportional to ds. If you increase the size of ds, then what happens? More number of lines are included. So your flux depends on ds. What are the other factors influencing the flux? What are the other factors? One is, yeah, you can see this on the slide as well. Yeah, you see here. There are three factors which are influencing the flux, magnetic flux, phi b. Okay. Yeah. One is last one, you see on that slide, area. Okay. It depends on the area. Just now I wrote here. Okay. Next, what other factors are influencing the magnetic flux? See the orientation of the. You can see the second one, the orientation of the ds, the orientation of the ds. See, if you orient like this, then how many lines will pass through it? Only one line. Instead of two lines, only one line will pass through this. Only one line will pass through this. So this orientation is also important. Orientation is also important. So this phi depends on this theta or cos theta. Theta or cos theta. Next, this phi also depends on the first thing in the slide. You can see here density of flow, density of the field lines. I already told you that what is density? Density of field lines is nothing but the field intensity of the field. Okay, if you are taking the strong field, then your flux will be more. So it depends on field, that means B. So your flux through ds depends upon these three factors. Okay, flux through some particular area will depends upon these things. How much is the area is, what is the angle between, what is the orientation of the ds, okay, theta or cos theta, what is the intensity of the field, okay, where the ds is located. Okay, all these things will influence the phi b. Phi b, let us write phi b, phi b. Okay, what factors are influencing this phi b? I will write here. Phi b is proportional to, as I already told you, ds. Phi b is proportional to theta or cos theta orientation of the ds. Next, phi b is also proportional to the intensity of the field. Suppose we take the same ds, but here we are having some different field. See, here the field intensity is more, say B prime, field intensity is more. That's why in the same area, see the object with the same area, see encircling so many field lines. Why? Because field intensity is more. So flux also depends on the field, local field intensity. Okay, that is B. Now, yeah, these are the three factors influencing the flux. That may be electric flux or the magnetic flux. Okay, B. So phi B is now B ds cos theta. B ds cos theta. You may write this. You may write this. Yeah, whenever you are taking ds, small component of area, this flux corresponds to that area. That's why we have to write d psi b. So here, this is the expanded form of vector b dot vector ds. So d phi b is equal to, you are having vector b dot vector ds. So phi b is equal to integral b dot ds. So phi b is equal to integral b dot ds. Now you see in the slide, this orientation with respect to what? External field. See, orientation of the surface means the orientation of the surface is given by the ds vector, which will always be perpendicular to that surface. Okay, so the orientation, to speak strictly, the orientation means orientation of ds with the b, external field, theta. Okay, you can see that in the diagram. In that diagram. Okay. So phi b is equal to b dot ds. B dot ds or b ds cos theta. Okay. Otherwise, you may take this ds cos theta as one component of ds in the direction of b also. Okay. Right. So the magnetic flux and magnetic field are related by this equation. Similarly, electric flux phi E is given by integral E dot ds. Electric flux is given by integral E dot ds. These are the similarities. See, these two formulas are exactly similar. Just we are replacing E with B or B with E. Okay. This is about the magnetic flux. Magnetic flux. The theory behind electric flux and magnetic flux is same, but the source field is different. There we have electric field, here we have magnetic field. Okay, right. This is about the magnetic flux and the magnetic field. Magnetic field, right? What are the SI units for magnetic flux? Weber. Weber. We measure the magnetic flux in Webers. Okay. Yeah. So magnetic flux will show you the presence of a magnetic field. This magnetic flux in a magnetic field depends upon three factors. One is the area of the dimensions of the area chosen. Next, the orientation. Next, the local field intensity. Local field. Okay, that's why we may express the magnetic flux YB as integral B dot ds. Okay, all these factors are included in this formula. This formula is very similar to the total electric flux formula. Phi E is equal to integral E dot ds. Okay, yeah, two things here you have to remind. Whenever the current is passing through a conductor, how to know the direction of magnetic field? By using the right hand thumb rule. You just hold the wire with your right hand such that the current is passing in the direction of your thumb. Then the direction of your fingers will show you the direction of a magnetic field, induced magnetic field. Okay, that is one thing. How to know the direction of magnetic force? Okay, you just bring the direction vector, direction of motion of the charged particle onto the magnetic field vector with your fingers, with your right hand fingers. Okay, then the direction of your thumb will give you the direction of the magnetic force acting on the charged particle. These two things you have to remember. This is very, very important also. Because B and E are vectors, we must have to determine the direction of those vectors. Okay, right. Okay, let us stop with this. Thank you.